Greetings, the Astro 30 here, and welcome back to AEL. Now, if you're new to this channel, please consider going down below and subscribing if you haven't done so already. Cheers. Today I'm going to look at a video I started recording about 3 years ago and never finished. It was on a Class B, which is kind of a misnomer because it's not actually Class B, 45 watt amplifier, which I found on Extreme Circuits. There's a few problems with the schematic out of the gate, which we'll go through. But I'm going to build it up on breadboard and test it, not necessarily with the original components, but basically get the circuit working and, you know, see if it's a viable circuit. So let's get into looking at the original schematic. Now, I was scouring the internet, as you do, for something else, and I came across this very interesting power amplifier circuit. The original article is called a 45 watt Class B audio power amplifier, and I'll put a link in the description where I found this schematic. Now, at first glance it looks very promising. It looks like a pretty typical discrete power amplifier layout, but there is one little issue with this schematic, and I'm going to stop talking for a second, see if you can spot it before I tell you. Well, if you haven't got it yet, this output stage looks weird. Why do I say that? Because the bases of these two transistors may be joined together via this capacitor, but they don't go anywhere else. These are the drivers, and this is supposed to be the output stage, but the bases aren't being driven by anything. They're currently reverse biased by the supply lines on their bases, but that's it. For all intents and purposes, these two transistors are big ass flyback diodes. What do I mean by that? So what I mean is, you've got your driver transistors, your supply lines, that's your negative feedback side, that's your output side. Basically all those two transistors are doing, from my own personal opinion, is acting like giant flyback diodes. So I can't see how that as an output stage would work. So I'll explain the rest of the operation of the circuit first before we worry about the output stage. Now, this is based on a Douglas Self design. It was originally a Class A amplifier. These two input transistors here are forming a long tail pair, and the output is taken off of the collector of Q1 as per usual, and R7 and R6 form the negative feedback loop, and with those current values, which is 22k for R7 and 1k for R6, that gives the amplifier a gain of roughly 23. Up here are our constant current sources. This transistor Q3 supplies a constant current source to the long tail pair, and Q4 over here provides a constant current source to the voltage amplifier stage, and there is the voltage amplifier stage I just mentioned, Q5. Now all these transistors up until this point are just small signal transistors. I'm not sure how well that one's going to work as a VAS or how hot it's going to get, but it remains to be seen. In between the constant current source and the VAS, we've got these two self-biasing diodes for the output drivers. So we've got a BD139 and a BD140 respectively. in a typical emitter follower class AB design. And then we've got that weird looking output stage, which I still can't see how it would work. Now, reading the whole entire article and looking further at the bottom, there's a little update here. There is a little mistake in circuit diagram. Q8 and Q9 are displayed on wrong places. In other words, they're transversed. Please replace Q8's place with Q9, and Q8 is an NPN transistor 2N3055, and Q9 is an MJ2955 PNP transistor. Please update your notes. So here's the corrected schematic, and it's more of a class AB amplifier than it is class B because of the way it's biased. But this is how the output stage should be wired. And now I have left a comment on that original post, which was from back in 2013, I believe. But it's still awaiting moderation, etc. Explaining his errors. But I've gotten rid of the resistors that were here in the collector paths of these two output stage transistors, because he had like 7 ohm there, and they're only quarter watt too. So you've got a 7 ohm resistor in the collector path of a high current output path here, because this is what produces all the current. Those resistors are just going to fry, especially if you start trying to get to the 45 watts that it purports to be able to produce. Yeah, okay. Not good. So I've changed them to 0.22 ohm resistors, and I'm going to start at 2 watt for this test. It should really be 5 in the end. But everything else is the same. So what I'm going to do is I'm going to build up the front end of the circuit up to the drivers, because this section here is actually an amplifier output. So you don't need this extra section here on the output for it to work. And just test that the actual input circuitry does actually work. I have made one substitution here. I've changed the 2 input transistors, which were BC560s, to BC559s, because I don't have any BC560s. There's not much difference in the 559 and the 560, so that's what I'm going to go with. And a lot of amplifiers that run on a plus minus 35 volt supply rail have BC559s as their input stage. The constant current sources are the same. VAS is the same. I've just modified the value of the Miller compensation cap to 100 picofarad, which is more standard than the value he had, which I think was like something like 15 picofarad. All the parts list of bill of materials is on the original article, which is linked in the description. So I'm going to spend about an hour building all these up. These diodes are all 1N4148s, so nothing special there. And we'll just see if we get an output just with the output drivers here without the output stage, because I don't really have any suitable high power output transistors to test this with. Well, not ones I haven't blown up anyway. So let's get on with doing something constructive. So more like half an hour later, I've actually got the circuit built, the front end. These are the 2 drivers. They've already got heat sinks on them, so that's not too bad. So I can do some basic tests with these BD139 and 140 transistors respectively. And I'll worry about a output stage later. Ignore these 2 capacitors, they're not actually in the circuit. It's powered up currently, around about plus minus 15 volts, just for a preliminary test. The scope is monitoring the output, and if I touch the input point, look at that. It's actually working as an amplifier. So it might help to hook up a signal generator to this to actually test it properly, which is what I'm going to do next. Signal gen's hooked up to the input and turned on to 1 kilohertz, and yeah, we do have an output signal, and it's relatively clean. Now the circuit's being tested unloaded at the moment, so it's not going to give us really valid output power measurements, but it gives us an idea of how well the input stage and drivers are working. And even unloaded, we're not drawing that much current, so that's alright. Oh, there's clipping there. So the next best thing to do, well, the thing that we should do, is put it into an 8 ohm dummy load and then to a 4 just with the drivers, see how it performs. And then I'll hook up a makeshift output stage to it. I've got a couple of TIP 41 and 42Cs knocking about on a heatsink, which will give us a bit more power output. Not much in this instance, but it just proves a point. Dummy loads hooked up into 8 ohm configuration. We still have an output, but how much power we can get out of this is, well, probably about a watt or so. It's starting to clip, and it's clipping asymmetrically, so it's not even clipping symmetrically. So what I have to do is increase that so I can see what I'm doing. But we can see how much of a voltage reduction we get when we go into a load. Now currently we're getting 1.81 volt RMS out, which currently is only producing about half a watt, actually 400 milliwatts. But yeah, it's understandable because it's not actually got a proper output stage on it. So let's see how stable this thing is into 4 ohms. So that means I need to move my ground connection to over there. And I need to move that to there. Now, without moving the oscillator amplitude, we can see that it's clipping asymmetrically again, so I'll back it off. Yeah, so we've got more like 858 millivolt into 4 ohms, which is, yeah, absolute crap. But that's only just coming off of these drivers, which are getting considerably warm. So what I'm going to do is, and plus don't forget we're on plus minus 15 volts. If it was a lot higher voltage, we get a higher output. But as I say, we're just doing preliminary tests here. So what I'm going to do is I'm going to, switch my load back to 8, and I'm going to incorporate an output stage now. I do have one knocking about somewhere. When I can find the bastard, I will hook it up. I just don't remember where I put it. Anyway, I'll go find that, hook it up, and do the test again. Alright, the output stage is now connected, so all the power is going through these two transistors, and these should remain pretty cold. The oscillator is sitting still where it was when it started asymmetric clipping, but we've actually got a higher output voltage, but I don't have a Zobel network in, so we're starting to see some ringing in the output. So I'm going to have to correct that in just a moment, but let's see what this goes up to. So I'm going to say there, and actually without a Zobel network it is relatively stable. So plus minus 15 volts, we've got 7.41 volt RMS, which is 6.8 watts into 8 ohms, which is a little bit more impressive than that op-amp based amplifier I built using the same components roughly. That's pretty good. So what is it into 4? So I'll just move the grounds. We're asymmetrically clipping, as we can see, so I'll back that off. 6.22 volt RMS. We get about a watt more, which is okay, not bad. Current draw is around about the 600 mA mark, which is, yeah, alright, that's pretty average. Now I'm going to switch back my grounds to the 8 ohm load, and I'm going to increase my voltages because I know it's safe to increase it. Not much is happening to the output signal, which is good, and that's the max of the supply, which is 17.5. Still got an output signal. It can go up a little bit higher because there's a higher voltage, and I can't go any lower on the scope, so I need to change to times 10. And excuse my big meat hooks. Okay, so that will give us a better, so there we go. So we're more like 8.73 volt. I don't think there was much of an increase. Yeah, it works out to about a watt more, 9.5 watts. But to get 10 watts out of a plus minus 17 volt supply into 8 ohms, and probably looking at about 11 into 4, from transistors which aren't really designed to be used as an output stage, because they just don't have the current capability, that's pretty good. Now, speaking of output transistors, in this instance you could use whatever you want, as long as they've got a current capability of at least 10 amps and like a 100 volt collector to emitter capability, rather than using TIP 41 and 42C respectively. I mean, you could use, not that I recommend using them anymore, but TIP 35 and 36C. You could use TIP 2955 and TIP 3055 if you can find some genuine ones. But yeah, and this is working quite flawlessly without a Zobel network. You could still include one. I have forgotten to put the 220 nanofarad capacitor across the bases of the output stage, which I will do now. I've added it now, and the output is still stable. So all that capacitor does is just keep the output stage stable. But however, it's still stable without a Zobel network. But it would be a good idea to include it. But anyway, I've proven that the circuit does work. The only substitution I made here is a 10 microfarad electrolytic input capacitor, because I didn't have a 1 microfarad knocking about, and a 100 microfarad AC feedback gain capacitor here. I can't even think of the term for that in the circuit anymore. It's where you got the feedback resistor coming off the output to the gain set resistor, and then between the gain set resistor and ground you have a capacitor. So it's like AC coupling, something like that. Anyway, 100 microfarad instead of 47, because I didn't have a 47, but it doesn't really affect the operation of the circuit that much, as we can see. So the original circuit is designed to run on a rather weird supply rail of plus minus 33 volt. Okay. But it should run at plus minus 35 just fine. And we've proven that it can run at as low as plus minus 15, although you won't get as much output power. But is it me, or is that rounding off at the bottom weirdly? I don't know, I'll have to check that by changing the time base. No, looks alright. We do have a little bit of ringing going on here between the crossover point. Yeah, we can see that the top peak is starting to ring, and even though my scope is not triggering, I bet if we added the Zobel network in there, that would clean that up. So let me just quickly add in the Zobel network components. As messy as that is, it's in. So that's with the Zobel compensation network in. That's with it disconnected. Connected? Disconnected. We can see a big difference in the signal there. So yeah, it does need a Zobel network, but that's perfectly fine, and was to be expected. So yeah, it's amplifying okay. It's certainly doing what it says on the tin. That bracket's getting mildly warm. Load's not doing anything. So yeah, even though the output stage was completely messed up on the original diagram, it does actually work. And I found this whilst trying to look for another amplifier circuit, and came across this, and then was a little bit confused by what they were doing with the output state. It's like, how can that even possibly work? Well, it can't. And I wasn't even going to bother hooking it up the way that they had, because, well, what's the point? Because we know it's not going to work, and we're just going to be wasting our time doing it. So I'm just cleaning some stuff up here as I'm talking. So yeah, it needed to be corrected. Whether my comment will go public on that forum site, I don't know. But I did say a few things, and I said I was going to test it but haven't done so yet. But I have now. So I can confidently say, yeah, the input circuitry works just fine, but his output stage is messed up, which was pretty obvious when you looked at it anyway. It's been running for quite a while now, about 10 minutes or so, at full power. Output stage is toasty warm, fast transistor, barely even registering any temperature. Constant current sources, not even hot. So from a design perspective at the moment, it seems to be functioning with the transistors it's got. So what I want to do now is, no one would forgive me if I don't do the customary sound test into a speaker. I also want to see if it makes any strange, weird noises, or like turn on transients, etc. And so let me hook up the test speaker, get rid of the load, and oscilloscope, etc. And we'll come back with a sound test, first with the oscillator and then with some music source. So it'd probably be a good idea to look at what the DC offset on the output is before going any further, because I haven't done that yet. So the multimeter is connected across the output and the load is off. Turn the load on. Oh, perfect. There's nothing wrong with that. That's great. Alright, speaker is hooked up, oscillator is still going but turned down. Now, this has no short circuit protection, so you have to be very careful when hooking things up like this, that they don't short, which they're not. So let's see if we have any weird turn on transients. Not really. Sound wise, does sound kind of nasty. Not sure why. Let's see. I'm going to change that to a lower frequency. 440 should do. Yeah, okay. I think it's the wiring. Yeah, that wire there. It does sound like it's oscillating a bit here. Right, that's as good as I can get that. That sounds better. It's just the wiring. So let me hook up an input signal and we'll try some music. Sorry, that took a bit to set up. Doesn't sound too bad. Kind of a boring track, isn't it? Kind of reminds me of Unsolved Mysteries. I think that's what they based it off of. The track's called Sacrifices. Anyway, that little circuit is working great. I'm quite happy with the results. I'm going to turn it off now. A little bit of a turn off transient there. That's fair enough, I suppose. So, yeah, I'm not sure what I'm going to do with this. I'm not going to sit there and, well, I can, if you like, design a PCB for it and test various different output stages on it. But I think I've actually made enough amplifier PCBs so far on this channel. I don't really want to keep doing the same thing. However, if there is interest in it, I can certainly, route out a PCB and make it available for people to purchase. But the whole entire point of this video was to actually take a design that's on the internet, test its validity, that's a hard word to say, validity, and see if the thing actually works. Now, it wasn't going to work with the output stage in its original configuration because it's drawn incorrectly. But it does work in this configuration when the output stage is in Darlington configuration here. For what it is, for what I found on the internet, it works okay, and I'm not really going to do any modification to it, so there you go. So if you enjoyed this video, please remember to go down below, like, comment, subscribe as usual if you haven't done so already. And this is the Astro 30 saying, see ya, have a great day. I'm going to start again. Greetings, the Astro 30 here, and welcome back to AEL. Now, if you're new to this channel, please consider going down below and commenting. No, you don't. Okay. Now, if you're new to this channel, please consider going down below and liking. No, fuck no.